The next property of a best estimator is sufficiency. In order to discuss this property of sufficiency, we consider a sample x1, x2, etc. xn taken from a population with a density fx theta. Here theta is the parameter of the distribution and our aim is to obtain a sufficient estimator of theta. For that we propose a statistic t, which is a function of x1, x2, etc. xn as an estimator of theta, that is t of x1, x2, etc. xn. Here we note that the variables representing the sample x1, x2, etc. xn will assume n dimensional values. At the same time, the statistic proposed t takes only univariate values. For example, if t is sum of the values obtained by x1, x2, etc. xn, then the sum has only single valued random variable. So for this can be illustrated with the help of a sample x1, x2, x1, x2, x3 taken from a Bernoulli population. Here x1, x2, x3 represent the response of three informants over possessing a characteristic. If they possess the characteristic, we will record 1, otherwise we will record 0. Therefore, the triplet x1, x2, x3 has values like 111, 110, 101, 011, etc. 000, and it has the triplet 111 if all the three respondents possess the characteristic, and 000 if none of them possess the characteristic. Thus, the values taken by x1, x2, x3 are three-dimensional values. At the same time, we define a statistic, say t, as x1 plus x2 plus x3. We note that the values taken by this random variable t, or the estimated t, are 0, 1, 2, 3, or univariate random variable. So there is a property, or there is a transition of three-dimensional random variable to a one-dimensional random variable, or this function t condenses the three-dimensional values to a one-dimensional value, and therefore T induces a partition of the values taken by x1, x2, x3 into four compartments. The first compartment 0, 0, 0, that is for the value of the statistic t equals 0. The next compartment is 0, 0, 1, 0, 1, 0, 0, 0, 1, that is for the value t equals 1. Likewise, the total values taken by x1, x2, x3 have been partitioned to certain compartments. So naturally we suspect that the information contained in that uh, triplet x1, x2, x3 has been transformed to the statistic T. Therefore, this sufficiency property deals with this loss of information during this transformation from an n-dimensional random variable to a single valued random variable given by the estimator. If no such information about that parameter theta contained in that n-dimensional random variables not transformed, no information is lost while transforming that to a single valued random variable or estimator, then the t is said to be a sufficient estimator. Therefore, if we consider here if any loss of information regarding the parameter theta contained in the sample lost when we transform that n-dimensional to one-dimensional, that is considered in sufficiency property of an estimator. An estimator t is said to be sufficient if all the information contained in that x1, x2, etc. xn regarding the parameter theta is contained in that statistic t also, then that is a sufficient estimator. Here t can be considered as a totality of or a representative of all the information contained in that sample variables x1, x2, etc. xn. Thus we have the definition of sufficient estimator. uh, x1, x2, etc. xn be A sample drawn from a population with the density function fx theta, where theta is the parameter of the population. An estimator t is said to be a sufficient estimator if and only if the conditional probability distribution of x1, x2, etc., xn given t doesn't depend on the theta for any value of the estimator t. This stating this conditional probability distribution doesn't depend on theta means that there is no influence of this x1, x2, etc., xn on the parameter theta when the value of the statistic t is given to us, which means that what all these x1, x2, etc., xn can do regarding the parameter theta can be done by that estimated t also. Thus, the values of the random variable x1, x2, etc., xn themselves do not contribute any further information when the value of the statistic t is given to us regarding the parameter theta. So, we say that t is sufficient to estimate the parameter theta in the place of this x1, x2, etc., xn. Thus, t becomes a sufficient estimator. Now, we have a set of conditions to examine this sufficient property of an estimator proposed by Fisher Neyman factorization theorem. But before that, we consider the concept of likelihood function. Likelihood function is a multivariate probability distribution. Multivariate means we consider more than one variable simultaneously. Here the variables were taken as the variables representing the sample. So if x1, x2, etc., xn represent uh, a sample drawn from a population with the density fx theta, then this joint probability distribution of x1, x2, etc., xn is addressed as likelihood function, and it is denoted by L. For example, if you consider a sample x1, x2, etc., xn taken from a point binomial population, definitely each of these variables x1, x2, etc., xn will follow point binomial distribution. Our aim is to obtain the joint probability distribution of x1, x2, etc., xn, that is a multivariate random variable. Here we consider the probability of the first variable x1 equal to x1 and x2 equal to x2 and x3 equal to x3, etc., xn equal to xn, that is given by this equation, that is probability of x1 equal to x1, x2 equal to x2, etc., xn equal to xn, and they are separated by commas. Therefore, here we deal with the simultaneous occurrence of values of n random variables. And since at the same time we note that this x1, x2, etc., xn are independent because that x1, x2, etc., xn represent a random sample. Therefore, to obtain a joint probability distribution, when the variables are independent, we can take it as the product of individual probability distributions. That's why in the next step we have the individual probabilities x1 equal to x1, x2 equal to x2, etc., xn equal to xn. Or this can be represented as a product of f of xi theta, because each of these xi's have the distribution, they have the distribution of the parent population, that is fxi theta. So it is pi I is equal to 1 to n p raised to xi into 1 minus p raised to 1 minus xi, or we can simplify it as p raised to sigma xi into 1 minus p raised to n minus sigma xi. This is the likelihood function, or in short, it is a product of n density functions, and these density functions are the density functions of the sample x1, x2, etc., xn taken from the population. We have one more example representing this likelihood function of a sample taken from a Poisson distributed population, that is x1, x2, etc., xn is the are the variables representing the sample. Then each of these variables are drawn from a Poisson distributed population, therefore their individual distributions are also Poisson. So we have that likelihood function L of x1, x2, etc., xn, that is P of x1 equal to x1 comma p of x2 equal to x2, comma etc., comma xn equal to xn. So since the variables are independent, it is the product of individual density functions. So we have e raised to minus lambda, lambda raised to x1 by x1 factorial, e raised to minus lambda, lambda raised to x2 by x2 factorial, etc., e raised to minus lambda, lambda power xn by xn factor, which can be further simplified as e raised to minus n lambda, lambda raised to sigma xi, and pi I is equal to 1 to n xi factorial. Thus, likelihood function is a multivariate probability distribution, and it is the product of n density functions because the variables considered in that multivariate probability distribution are independent to one another. Next, we have the Fisher-Neyman factorization theorem, which offers a criteria to examine sufficiency of an estimator. For that, we have a sample x1, x2, etc., xn taken from a population with the density fx theta. Then theta is the parameter of the population and t be an estimator proposed to estimate the parameter theta. We consider the likelihood function of the sample, that is L of x1, x2, etc., xn, comma theta. Then this t is a sufficient estimator of theta if this L can be factorized into two functions. That is, one is the function L1 and the other is the function L2. And in L1, the t and theta must be present. Only t and theta must be present. And L2 is a function independent of this parameter theta or that parameter being estimated. So we take L as product of n density functions. After simplifying this likelihood function, we must be able to write it as product of two functions. One is L1. In L1, the estimator proposed and the parameter theta only be present. And also constants are permitted in any function, either in L1 or in L2. There is no restriction for constants. The restrictions are only for the parameter and the estimator and some other function of this sample also, that is some other statistic. So in L1 we have only the proposed estimator and the parameter theta, and L2 is independent of the parameter theta. Then t is said to be a sufficient estimator of theta. So the first factor is a function of the parameter and the estimator proposed. Second factor is a function of this x1, x2, etc., xn only. Then t is said to be a sufficient estimator of theta. We can examine the sufficiency property of an estimator using this Fisher-Neyman factorization theorem.